Let's get started with the presentation on what's new in FICO Xpress 9.6 Solver. So we start with my traditional first slide for every release webinar, which shows that FICO Xpress optimization consists of various components. So they all build on top of each other, they nicely integrate within each other. And you, as one of our users, might enter the stack that we see here at different levels. So maybe use one of our business solutions, or you might directly work with our software components. So you might develop your models in Xpress Workbench, our in-house IDE, and deploy them via Insight to cooperate with your colleagues on the cloud. Maybe you develop your models in Moselle or Python, or you use the solver via one of our many APIs in various programming languages like C, C++, C#, Java, and so on, which have recently been nicely unified to all have a common look and feel. And anyhow, in the end, all of you use our solver directly or indirectly, one way or the other. And yeah, the solver is the core of Xpress optimization. And in the next 45 minutes, I would like to tell you what news and what new features there are in the latest release of this solver. So we have a packed schedule for today with many new cool performance topics for our MIP solver, like a new type of heuristics, changes to the way how cuts are separated, a better pre-solving routine. And we got news from our primary dual hybrid gradient solver, some nice improvements from our symmetry detection via LP folding. Our global solver has seen a lot of performance improvements as well. And yeah, that's by far not all. There are also many new features like our deterministic work controls and attributes, a genuinely new way of licensing Xpress, new callback, and a more streamlined Python interface. So without further ado, let's kick this off with a topic that's always close to my heart, MIP solver performance improvements. Okay, so one exciting new development is our pre-root parallel heuristic, which runs before the initial LP relaxation. So as a business use case, consider you want to solve problems where you would be happy with some reasonably good solution. You don't really require a proof of optimality, but for your problem, just solving the initial LP relaxation takes as much or even more runtime than you would want to spend. So in this situation, you would likely be in trouble with all the Xpress versions, because before the LP, we so far only use some trivial heuristics, which, if at all, mostly produce, clearly suboptimal solutions. And for the, say, good heuristics, you would have to wait until after the LP. So now you have this new option, pre-root parallel heuristics. And this heuristic phase is highly parallelized, as the name already gives away, making full use of all available threads, and it employs randomization to diversify the search. It doesn't require an initial LP solution, and this means that it can be run before the initial LP and operate essentially right after pre-solve. So yeah, it's off by default, but it can be enabled via controls that are not on this slide yet, but I'll explain them later. And yeah, anyhow, the goal is to alternate between improving feasibility and the objective value. And the inspiration here comes from the so-called alternating criteria search methods, essentially conducting large neighborhood submip searches. So the heuristic fixes a subset of variables, or the different heuristics that work in this phase. They solve the reduced MIP, improve some of the solutions, and iterate between improving the feasibility and reducing the objective, improving the objective, the original objective of the MIP. So we also incorporate some of our existing local searches like shift and propagate and the feasibility jump into this heuristic phase. And also, if an initial feasible solution is available post pre-solve, it will be immediately used, like for example, a solution given by you, the user. And if not, these heuristics will start from randomized, likely infeasible integer solution candidate vectors. So the main heuristics essentially alternates between two types of solve, one aiming at reducing violations, so that's the feasibility phase, and another aiming at improving the objective phase. So this involves setting penalties on violations and fixing certain variables to focus the search more efficiently. And the parallel nature here means that different threads run different subproblems simultaneously, and then and all of this then single-threadedly, and then solutions are combined using a crossover step, refining the solution further. So all these single solutions go into some combined solution, and here the same again. So you will start this with a reference input solution, and then always loop between the feasibility and an objective phase. And in both of the phases, problems get split up into subproblems, and at the end, the solutions that each of the subproblems can merge together again, as I already said. So, and how the splitting into subproblems work, how the solutions come back together, and what other heuristics run on the side, this is, in a sense, the secret sauce of these relaxation-free heuristics, if you want. So, as for enabling this phase, it's off by default because it's most beneficial on large problems with slow initial AP solves, but detrimental for problems where you find good solutions anyway directly after the AP and where you solve the AP quickly. So if you want to play with it, you can activate it using the euro emphasis control, for example. So setting it to 2 enables this heuristic and also a lot of different other heuristics that we already had present previously. So heuristic emphasis equals 2 used to be a thing already before. It just now incorporates these parallel heuristics. And then alternatively, if you just want to dedicatedly work with this particular heuristic, you can do so by controlling the effort explicitly using pre-root effort, or set a deterministic work limit using pre-root work limit as control. And what this term work here is about, I'll again explain later when it comes to our new features. Okay, so performance-wise, this heuristic significantly benefits harder problems, ones where solutions are tougher to find initially. And this improvement becomes clear when measured using the primary integral, our metric for measuring heuristic performance. There it's beneficial on average, and for a few problems, it's really a very big win. And on the right-hand side, you can see and this is how you could notice the heuristic in the log. So first you have a pre-solving and scaling, and at the end of the screenshot here, you see the start of our LP solving, the start of LP concurrent, and in between, you see pre-root parallel heuristics being launched and finding 1, 2, 3, 4, 5 solutions. So as a final remark here, note that this heuristic doesn't help to prove infeasibility. It's like many other heuristics solely aimed at finding feasible solutions or improving solutions early on in the search. Okay, moving on to other MIP topics. We are now separating global cuts within the branch and bound tree. So this topic might be interesting when you have problems where you need to prove optimality and likely have a huge tree search that needs to be carried out for doing so. So yeah, in a sense, that's kind of opposite to the previous topic where you would only do things in the very beginning and focus on primal feasibility. So anyhow, there's an important distinction for cutting planes about the scope where they are valid. So there are global cuts that are valid for the overall problem, so the solver can use them beyond the local problem where it generated them. And for being globally valid, of course, whenever there is a choice, the cutting plane generation method will need to use the global variant of some information. So for example, the original variable bounds, not the variable bounds at the local branch and bound node. And then there are local cuts. So local cuts are only valid at the node where they have been created and at all descendant nodes, so at the subtree rooted at the current node. And if a cut needs to be only locally valid, well, then the solver is free to choose which information it uses and will likely use the stronger and the more restrictive, the local variants, like the local bounds. So yeah, see the picture on the right here. The cut here is valid for the left subproblem, but yeah, because here it does not cut off any of the feasible black solutions, but it's not valid for the white subproblem. Here, two solutions will be cut off. And the global cut above, however, is valid for both problems and in fact globally. So it can be reused over here if you wish to do so. So that's the distinction between global cuts and local cuts, some technical background. And all of this comes with pros and cons. So the main benefit of global cuts is, well, they can be reused. So you don't have to regenerate them again elsewhere. You don't have to find the same or a similar cut over and over again. And also they do not get into the way of procedures like conflict analysis as local cuts sometimes do. Then they are typically weaker, as we saw in the previous image, kind of, since they are derived from less restrictive information. And well, of course, reusing and sharing does not come for free, but creates some synchronization overhead, at least in parallel search. And if you run a sequential Xpress, this will not be an issue. So previously, Xpress only ever generated locally valid cuts outside the root node. And now global cuts are separated and can be applied anywhere in the tree. And the synchronization overhead that I mentioned is minimal, but it exists. And this gives us, balancing this out, gives us an overall modest improvement of around 1% improvement at 16 threads. And I don't have it on the slides here, but if I remember correctly, obviously the less threads, the less synchronization. So the improvement becomes more pronounced, and at single threaded, I think it's something like 2 or 3% improvement, if I remember correctly. So, next topic, heuristics again. We've also made our fast branch and bound heuristics at the root default now. So this heuristic runs on a parallel thread in the background during the root node, so in parallel to the cut and heuristic loop. And it performs a fast branch and bound search in case the problem can be solved quickly using just some branch and bound, but no cuts, no strong branches, no other threads. And previously, we were using this only in our famous UR emphasis mode, where it is automatically running in the background, already has been doing so since 9.4, I believe. And we now use it by default, provided that there are enough threads available. And yeah, we also applied some other improvements to it, and it provides about a 2% improvement on hard problems, again, despite some slight overhead coming with it, as always, as you do something new in parallel. And finally, I would like to talk about a pre-solving routine. And this one affects mainly highly combinatorial problems. So, for example, if you have an application from cryptography, this might be interesting for you. So this pre-solving method considers short, purely binary constraints. And for such, you can very efficiently enumerate all solutions. Like for 4 binary constraints, that's 16 solution candidates to check, and you can do so very efficiently via incremental updates or via candidates. And if among those candidates there's only a small number of feasible solutions, you can check their feasibility for other constraints, and doing so might allow for all kind of reductions. So if all solutions in those variables have a certain value in common, then you might fix that variable to this value. Also, you might again find certain relations. So for example, that two variables always take opposing values. So taking the example on the right here, where there are only 2 feasible solutions out of 8 candidates, this is what these highlighting should indicate. You can directly deduce that the binary associated to this value here has to be fixed to 1, and the other 2 have to take opposing values. So call them x and y, then you can deduce that x is 1 minus y. So we had a variant of this already in place, of this pre-solving, enumeration pre-solving method, and we improved the implementation. Once again, we allowed for some shortcuts here and there, and we could therefore broaden its scope significantly. So this gave some very nice performance improvements, but mostly on some restricted classes of problems. So huge win on a relatively small number of problems. So let me also use this chance here to point out that in this release we worked a lot on low-level software engineering, like optimizing memory layouts, working with compiler flags, etc., and so on. And that contributed nicely to performance, but it's really nothing to pull up a slide for. Very technical, not very insightful, but this also contributes to our nice performance numbers that we will see later. So, and after all those integer topics, let's now move to some improvements in the continuous space. So, starting with a topic that is relevant in both areas, discrete and continuous. But yeah, our latest developments here have mainly affected the LP side of things. This is why I present this here in the LP performance section. So symmetry detection and particular partition refinement for LP folding has been completely rewritten inside Xpress 9.6. So there's a new graph-based algorithm that speeds up the detection from hours down to minutes in some admittedly extreme cases, and still noticeable, the speed up is still noticeable even on moderately sized problems. So yeah, furthermore, this algorithm is not only faster, but it also applies more generally, including dual LP problems, and potentially we might look into nonlinear problems in the future. Not yet, however. So yeah, let me use this occasion to give a reminder of the idea of symmetry detection, because I think that's really cool. So we would like to find out whether there are duplications of some identical structures within the problem matrix. So this is what we call symmetries. So it's something that likely many of you know from your applications. So there are identical items and you need to make assignments, but it does not really necessarily matter which item is assigned to which machine or to which vehicle, or a particular task is assigned to. Just you need to make some selection, and you could afterwards exchange some of the assignments for each other. So this is a typical example of a symmetry. So for this symmetry detection, we represent the model matrix by a graph, and then each column gets represented by a vertex here. And each row also gets represented by a vertex, and each coefficient gets then represented by an edge in this graph. And then we start coloring the graph to see which nodes and edges are similar to each other and which are different. So columns with identical objectives get their nodes colored in the same way. So everything that has an objective for 1 is colored red. Everything with an objective for 0 stays colored white here. Rows with the same right-hand side are also colored in the same way. And identical coefficients get colored in the same way. So far, so good. And well, now still not every node with the same color is the same. So looking at these two red nodes here, they have differently colored edges adjacent to them, and well, so they for themselves are equivalent, so to say, if you look at them in separation. But if you look at their neighbors here, they have differently colored neighbors, and they also have differently colored edges going out of them. So you know from that they cannot be symmetric to each other. So we can split these color groups into smaller groups by looking at their neighborhood. And then, well, we can repeat this whole process until there are no more updates. And the symmetry of this graph then tells us now that there are two copies of the same problem in our matrix and that we can reduce its size essentially by a factor of 2. So learning the symmetry of this graph is identical to learning the symmetry of this matrix here. And well, this process that leads to this graph coloring is the core of LP folding, and this is what has been improved in Xpress 9.6 to get the circle back here. Okay, regarding further LP and QP and SOCP improvements, our primary dual hybrid gradient method, or short PDHG, received some stability and convergence enhancements. So PDHG as an algorithm is tailored for large, highly degenerate problems. And while what barrier remains the best choice for smaller problems, PDHG sometimes drastically reduces solve times on very large instances, in cases again from days to hours or sub-hour. But sometimes is an important keyword here. So not only is barrier faster on average, it is also more consistent. So as of now, PDHG still fails to converge on many problems, even if this has improved a lot in 9.6. So rather read the messaging here as when PDHG works, then it can be much faster than barrier, but often it does not work that well in the first place. But anyhow, it's an interesting methodology to experiment with. So if giant LPs are your use case, you might want to give it a try and see whether your problems are among those models where it can handle them really well. So, and if you want to do that, if you want to play with PDHG, you can use the regular barrier controls to do so. You would activate it with these bar arc. I just noticed that there's an A missing here. So A for algorithm here to switch to PDHG. And yeah, so please drop us a note when you have instances where this technology could be relevant. These huge, potentially degenerate, potentially numerically challenging LP models. That's really very interesting for us to continue development here. And yeah, as this is relatively new, I mean, we're always interested in new test cases, but in this case, even more. I also would like to point out a blog post on a recent collaboration with NVIDIA on this topic, with some more news that might follow soon. So yeah, maybe Dinika, if you could also post this one into chat, that would be great if you haven't already done so. Okay, so we had integer and continuous topics, but so far everything was linear. So let's quickly look into updates on our nonlinear global solver. So for global solver and nonlinear improvements, all quadratic constraints and objectives now run through the optimizer pre-solve, so to the same pre-solve machinery that we would run our linear problems through, enhancing second-order cone detection and linearization of binary continuous products. So we've substantially improved the what's called reformulation linearization technique, or short RLT, cuts for continuous non-convex problems with some notably boosted performance. And we've also implemented some, let's say, adaptive feasibility tolerance adjustments during branching, and that enhanced the numerical stability of the global solver. Again, a lot of engineering, getting into a lot of gory algorithmic details that overall gave some really nice performance improvements. Okay, so let's now look into some features. So if you are a mathematical optimization aficionado, then probably this first part of the presentation that we had was for you. If you, however, are more from the pure user side and you want to know what can I do now with the solver that I couldn't do before, never mind how it really runs internally. Well, here comes now the presentation features. Let's get into them. So our new deterministic work attribute measures computational effort deterministically. This allows for consistent work-based limits independent of hardware variability. So yeah, as a business use case, this particularly caters to OEMs, for example, who look after reproducibility of runs, or also if you want to include partial MIP searches as subroutines into a larger deterministic algorithm, you now have a very direct way of setting effort limits in a deterministic fashion, which is nice. So previously, this might have been achieved by setting node limits or simplex iteration limits, but now our work limit control associated to the work attribute is much more finely granulated. So yeah, unlike the time attribute for two identical runs, which depend on external, so so like, let me start again. The time attribute, as void clock time works, depends on external factors like the workload from other processes on the machines. But then if you do identical runs and look at the work attribute, this will always deliver the exact same value. So like our other determinism guarantees this holds cross-platform and independent of the hardware, and likewise settings, a work limit will always make the solver stop at the exact same stage, which can be useful for some of you. And of course, the ratio between work and time then, this depends on the hardware. How could it be different? So faster hardware will get more work per second done. That's a direct implication on of the work is independent of the hardware. The ratio between time and work has to be dependent on the hardware. So very roughly, the idea, however, is that 1 unit of work is roughly 1 second, but as different computers can be twice as fast or 5 times slower, this really has to be taken with 2 grains of salt, and it really should only be in the same ballpark. 1 unit, well, let's say it's somewhere between 10 seconds and a tenth of a second or so. So in the picture, you see how we now output work in the log with the new log line. And in this case, the approximation is quite good. The solver got 0.7 work units done on average per second. So a total of 2000 work in 3000 seconds. And callbacks can query this attribute, enhancing deterministic callback timing, and we've added a deterministic callback delay via the callback check time work delay control. And the use case here is similar. If you want to decide interactively, but in a deterministic fashion in a callback, when to stop the MIP search by using the check time callback, then this is exactly for you now. Okay, and for those users that like to directly interact with the bunch and cut process, as we've just seen, so if you want to directly interact via callbacks, there is some news. We have introduced a new callback. The cut count callback is executed before any potential round of optimizer generated cutting planes. So this means it will trigger at any point where the optimizer considers separating cuts, irrespective of whether it eventually actually does so. So one important aspect of this callback is that at every node where the optimizer might perform cut separation, the callback fires and includes an argument that explicitly states whether the optimizer currently intends to separate cuts here or not. So technically, there would be an opportunity for cuts, thus the callback is fired. And the optimizer lets you know its opinion, whether it now would actually do cuts or not. And then users can override the optimizer's default decision here. You can either force the optimizer to proceed with cutting plane separations, irrespective of whether it wanted to or not, or you can explicitly prevent it from doing so. So additionally, this callback fires again immediately after each round of cuts, which is the natural next point to cut again. See the idea of a cut generation loop. Yeah. So you will receive another callback invocation allowing you to make the same overriding decision again. So you did a round of cuts and then you will be asked again, do you want to continue or not? Yeah, but this isn't the sole purpose of this callback. So within this cut count callback, we've introduced a new function called Xpress at managed cuts. So this function enables you to supply user-defined cutting planes directly to the optimizer. So unlike the previous methods that we had involving manual management of cuts, so such as using Xpress add cuts or Xpress load cuts, these new managed cuts are automatically incorporated into the optimizer's internal cut pool. And the optimizer then selects and adds the most violated cuts from this pool to the local node problem automatically. And moreover, the optimizer also handles the automatic removal of these cuts once they are no longer beneficial, ensuring some efficient and streamlined cut management. So this is a choice that you have to make, whether you want to keep control over your cuts, then you do it the traditional way, or whether you want to give away all controls, you don't need to worry about them anymore, but also the solver might just decide to delete them at some point. Then you use Xpress at manage cuts. Yep. And yeah, importantly, cuts added through Xpress at managed cuts are provided directly in the original user space, eliminating the need for you to manually pre-solve those cuts beforehand. And the optimizer automatically takes responsibility for pre-solving these cuts internally. So it really provides a significantly more automated, convenient way of managing user cuts compared to our more traditional methods where you previously needed to manage, add, and delete cuts at appropriate times, all on your responsibility. So while this callback is primarily designed for handling cuts, it also allows additional functionalities similar to typically node-related callbacks. So for example, you can add new solutions or you can also add explicitly managed cuts in this cut beds this callback using traditional methods like Xpress add cuts and Xpress del cuts. So however, we recommend reserving such explicit management for traditional opt-node and pre-install callbacks. So for a cleaner solution, keep these things separated. Moreover, we've added an associated attribute named cut rounds, which was missing from our set of attributes so far. And this attribute indicates how many rounds of cuts have already occurred at the current node, helping you effectively track the frequency of cutting plane separation. And then for all our clients who use Xpress in a virtual environment or work with containerized deployment, but also for everyone else who's interested, that there is a new licensing system. For now, this is in parallel to the existing one. It uses a lightweight, secure, fast, web-based authorization mechanism where license managers can see their entitlements in the new user portal, retrieve the credentials, and get notified about license and credential expiry. And this is new and bound to Xpress 9.6 and newer version. So if you want to use this licensing system, you need to upgrade your Xpress. And this slide really is mostly an announcement for our way more detailed webinar where my colleagues Dineka and Adam will demonstrate various use cases and ways how to leverage this new system. They will talk about web floating licenses, will demo examples starting from command line, Docker, Python, notebooks, Express Inside Compute, and much more in exactly 1 week from now, but on a different webinar. So you need to register extra if this is of interest to you. And again, I think Dineka might drop a link for that into the chat. Okay, so there have also been some updates to the Optimizer API. Our solution functions such as get solution, get duals, get slacks, get reduce costs now return a status argument explicitly indicating solution availability. So previously, these functions only returned the solver status, which could misleadingly suggest that no solution existed even when one was available. So, for example, if solving a MIP that becomes unbounded after initial heuristic solutions were found, the solution now correctly, or the status that those return now indicates the solution availability. So yeah, there is a solution, we found one, despite the solver status indicating unboundedness. So several functions also are now deprecated in favor of newer and more appropriate alternatives. So for example, Xpress order should be replaced by the relevant Xpress change functions. Xpress unload LP is no longer necessary. You can just load an empty LP instead if you just want to clear your problem. Furthermore, instead of separate functions for adding names to sets, the more comprehensive Xpress add names functions now uniformly handles naming across rows, columns, sets, other entities. So you can use that instead. Yeah, we also streamlined nonlinear API controls, particular for global solver and SAP, and showing some better alignment with optimizer defaults. So controls such as NLP threads and NLP pre-solve now inherit their values from the standard optimizer controls, and unless they are explicitly overridden by the user. Our Xpress post-solve function now also maps solution from pre-solved nonlinear problems right back into the user space effectively. And the functions Xpress set defaults and Xpress set default control now apply to nonlinear functions as well. So at a lot of places we have taken away this restriction of unless for global solves. So yeah, all of that has previously been limited. So yeah, moreover, XSLP minim and XSLP maxim functions have been deprecated, and please use the Xpress optimize and Xpress NLP optimize functions instead, as again on the linear side you likely have been doing for years now. So to switch methods, if you want to switching between minimization and maximization, can use our objective sense attribute for this. Okay, let's also look into some Python-specific changes. Easy things first, there are new Python and NumPy versions supported, and support for some old Python version has been removed. And the next one is a big unification step to get Python consistent with all other APIs. So previously we had a few constants defined only, but by far not everything that you would see in the C manual was available in Python. And those that were available did not very stringently follow a naming convention that was consistent with the other APIs, so that's no good. So now all the optimizer constants are defined using Python's enumerations. There's an enumeration for each collection of optimizer constants, and when you use those new constants, just as you would use the previous constants, they can just be interpreted as integers. The enums, the enumerations, they all live in the Express namespace. The concrete values, they live in the express.constants namespace. So yeah, also coming to a typical pain point with operator overloading. What does the equal sign mean? So when talking about mathematical modeling, one can easily interpret the equal sign as the equality sign in a model constraint, and stating x plus y equals z. This creates a constraint for the model that the sum of x and y must always be the same as the value of z. Logically, isn't it? Okay, but it could also mean that someone wants to literally compare two Python objects and want to know whether one expression object containing the term x plus y is the same as another expression object containing the term z. And that's not the case. So those are just two different items, logically. So for this ambiguation, we now introduced a way to switch between these two different interpretations. And we also introduced explicit functions if we want to make clear that we want to use one or the other independent of what the switch here says. So this might, for example, be important for unit tests on the user side. And finally, we have new functions on variables and constraints where you can retrieve the solution values, duals, reduce costs, slacks, and so on. Prior to 9.5, this wasn't really possible to have this in this easy and direct way because variables and constraints could belong to multiple problems. But now, since 9.5, we have these linked variables and constraints that just belong to a single problem, and we now can always query those values unambiguously directly from the variable or directly from the constraints. And again, much more details on this and many smaller updates and everything new on Moselle. You can learn the day after tomorrow, same time, different Zoom webinar. You should register separately. And lastly, documentation improvements were made for user convenience. Function controls and attributes are now organized into thematic topic areas within our documentation. So for instance, controls like our tree cut select now clearly belong to topics such as cuts and branch bound and bit vector controls, and then clicking on any topic lists all the relevant associated items, which I haven't bought here, could have included the screenshot. And this significantly simplifies your documentation navigation experiments. And yeah, I can really tell you this is a nice extra tweak to the documentation. So I, for myself, have started using this feature from day one since it was available. Look at the control. You want to see what other controls play in the same area, just one click away. Really nice. Okay, and now for the highlight of each release presentation, performance numbers. So this is our typical year-on-year improvement table that we always show in these webinars. So a year ago, the current Xpress release was 9.4, and this table compares our new 9.6 release against 9.4. So these are numbers on our internal benchmark set consisting on a mix of public and client instances, and those instances are sampled to avoid any type to dominate the benchmark. And we compare geometric means of runtimes here, except for the nonlinear SAP rows, where we compare the so-called primal integral, a measure for convergence speed of the primal solution. And our special interest is always on the harder models, where our in-house definition of hard takes more than 100 seconds to solve. And yeah, what shall I say? We are really happy with those numbers. The important solvers for LP, MIP, and MI-NP are all at least in the two-digit improvement rates year on year, with the most important benchmark, the MIP cracking the 20% bar, which is always really big for us. And this comes from the 3-4 technologies that I have presented in more detail today, but also from many small improvements that we really didn't have time to talk about. So a lot of things are going into this. And for our very new algorithms, where there is still a lot of ground to be gained, we see that PDHG became a factor of 3 faster, a factor of 3. And our global MI-NP solver almost a factor of 5, and both also solve way more problems to proven optimality than they did a year ago. So global optimization really becomes a business usable feature, and we're happy to see how different users already picked that up. Okay, finally, 45 minutes have passed. Let's do some announcements. Our Xpress Best Paper Award goes into its 4th year of existence. And yeah, we have a 2026 edition. So here you can hand in scientific papers that used FICO Xpress in their work and win yourself a nice little monetary prize and of course some visibility for your work. So follow the link if you want to learn more. The deadline is still some time away, but remember your paper needs to be published by then. Online publication, by the way, is enough and does not need to be published in print, but it needs to be in some peer-reviewed journal or some well-refereed proceedings value. And speaking of which, it is my honor to mention for the first time publicly the winners of 2025. That's Giuseppe Hirva and his team from Colorado with their paper on optimizing design and dispatch of a resilient renewable energy microgrid for a South African hospital. A really nice work where they go into all details of modeling and solving an energy optimization problem, how to get the data, how to adapt everything to local situations, how to evaluate it, and so on and so forth. Really nice. And we also have a runner-up, Puri Nicknam and team, curiously enough, from Birmingham, with their work on optimally integrated waste heat recovery through combined emerging thermal technologies, modeling, optimization, and assessment for onboard multi-energy systems. What a title, and a great paper as well. Congratulations. And we are all looking forward to blogs on both topics where the teams are already working on. So if you want to learn more about Xpress, check out all these places that are linked here. If you haven't already, so our optimization community, which collects blogs, training material, and all kinds of useful stuff around Xpress, our user forum, where we as the solver developers are very happy to answer your questions, and our academic partnership program, where academics can get free full licenses for Xpress for their research, maybe on a best paper award worthy topic, who knows? And finally, people who watch this webinar might also like those webinars. In 2 days, Susanne and Chris will introduce you to Moselle and Python enhancements. In a week, Adam and Dinaka will present our new licensing system, as already mentioned. And on July 1st, John and Alex will give a hands-on session on accelerating workflows with Xpress. So, folks, we've made it. Thank you so much